Previously, on So Much Code. There is one other very exciting use case for lambda expressions that I haven't mentioned yet. Remember that I said that if you want multiple output values, you could always have the first output return the first value that you want to return, and have the second output return a lambda expression that would then produce the next output. Well, take that to a logical conclusion, and let's see where we can go with that. As I'm sure you remember, in video number 7, we came up with a way of cramming as many integers as we want into a single integer in order to represent lists. So in theory, a list can contain any number of elements up to infinity, except of course infinity itself. And then in video number 8, we talked about lambda expressions, and I teased you at the end of the video to think about what we could do with lambda expressions if we take this to a logical conclusion. And I explained to you that the reason I wanted lambda expressions to have a single input but multiple outputs is because you can have a lambda expression with multiple inputs by using currying. But when it comes to multiple return values, I suggested that you could just return the first value in the first output and then have the second output return another lambda expression, which will then produce the rest of the values. Well, what we end up getting is a system where a lambda expression can return a value and then another lambda expression, and then that lambda expression can return another value and another lambda expression, and that can keep going any number of times, and eventually, instead of a new lambda, you can just return 0 to indicate the end. And look at what we've done. We've created kind of like a list, except that we didn't have to put it all into one integer. We didn't have to come up with an encoding. Instead, it is all built on top of the infrastructure of lambda expressions. Since this is not the same as lists, I decided not to call it lists. Instead, I called it lazy sequences. Now, sequences, obviously, because it's a sequence of numbers. Why lazy? I'll come back to that later. Another thing we talked about in the lists video is these two fundamental basic operations. We use the unshift function to basically create a list. You can start with the empty list, which is just 0, and then you can build lists from there. And of course we use the shift function to take the list apart again so that we can read the elements that are inside of the list. Any other function that we want to write for lists, such as for example one to find the nth element, or reverse a list, or whatever, is all built on top of these two fundamental instructions, shift and unshift. So logically, that means that if we find other operations that do conceptually the same thing, which is to prepend an element to the start of something and return the first element and the rest, then we can do everything that lists can do. All we would have to do is just rewrite all of the functions. Okay, let's take a look at the unshift function which we needed to create a list. So what we're asking is, how do you take an existing lazy sequence and put a new element at the front? And the answer is as simple as it is elegant. All we need is a single lambda expression which will simply return the new first element as its first output, so that now becomes the first element of the sequence, and the sequence as its second output, so that becomes the rest of the sequence. And since it doesn't matter what you pass into these lambda expressions, I'm just silencing the input. And how do you get those elements back out of the sequence? Well, because the sequence is a lambda expression, we can actually just call it using a lambda invocation box. And since it silences its input anyway, we can pass in whatever we want. In this case, I'm just passing in 0. And of course, the first output that it will generate is the first element of the sequence, which is the head, and the second output will be the tail, which is the rest of the sequence, or 0 to indicate that the sequence ends here. You may recall that in the previous video I said that lambda expressions are always allocated a non-zero value, and now you understand why. It's because I use 0 to indicate the absence of a lambda expression. Here's the map function that we wrote for lists in the previous video. This was our first function that uses lambda expressions, right? It calls a lambda expression on every element in the list. But it still uses the shift and unshift function to take the list apart and then put the new list back together. Well, here's what the new map function looks like. This time we're using a lambda invocation to obtain the head and the tail, and you can see how in the list version the head element goes into the provided lambda expression. And the same thing happens here. The first element just comes out here and goes straight into this lambda invocation, which just calls the lambda that is provided as a parameter. Similarly, the tail of the list just goes straight into this recursive call. The same thing happens here. The tail of the list comes out here and goes straight into this recursive call. And then in the list version, of course, we use the unshift function to put the list back together, which here we do by declaring a new lambda expression. You can see that the new head of the sequence is the result of that lambda expression that was passed in, and the second output, the rest of the list, is the result of the recursive call. So you can see that the structure of the function is basically exactly the same. And as I'm sure you've already guessed, the same is true of the filter function. Now I'm not going to go through the entire function here, but you can definitely see the resemblance. You can see that the result of the lambda expression, which is the filter criterion, goes into a question mark box in both cases, and the result of the recursive call goes either directly into the question mark if we want to filter out an element, or into the shift function if we want to keep that element. Similarly here, the result of the recursive call either goes directly into the else case of the question mark, or it goes into this lambda expression, which uses it as the rest of the lazy sequence. But now let's have a deeper think about what actually happens when the map function executes. Of course, the list version of the map function, well, it needs the unshift function to take all of the elements out of the list, and then it uses the shift function to create a new list. And it has to create the entire new list before it can return it, because there is only one return value, which is the complete list. Meanwhile, in the new version of the map function, we're just returning a lambda expression. So what that means is that this function will not actually perform the recursive call. It's the lambda expression that will perform the recursive call, and it will only do so when invoked. To see why that is incredibly beneficial, let's just imagine you have a long list of a lot of data. Now you want to use a map function to turn every element into some other new element, and then maybe you want to use the filter function to filter some of those elements, and then you just want the first 3 of those. You can immediately see how the list version produces a lot of data that does not actually get used, so there is a lot of time spent producing that data when we don't need it. Whereas if we do the same thing with lazy sequences, then we only need to generate the items that we need, and as soon as we've generated the 3 items that we want, we can stop, and all of the rest of the processing just doesn't happen. So there is a massive performance benefit here. On top of that, another massive benefit is that your lambda expression, when it returns another lambda expression, it doesn't really have to be a different lambda expression. Imagine just hypothetically, it returns the same lambda expression every time. What do you get? That's right, you get an infinite sequence that never ends. You can never have that with lists because you can't represent that in an integer that is still finite. But since lazy sequences are lazy, in other words, they only execute when needed, we can have a lambda expression represent an infinite sequence, and there's nothing wrong with it. It doesn't automatically create an infinite loop. It only creates an infinite loop if you write a function that actually tries to find the end of this list. Now here's a very simple function that will just return a lazy sequence containing only a single value. It's literally just a lambda expression that just ignores its input, and its first output is the value that we give it, and the second output of course is 0, which indicates the end of the sequence. But now let's look at this slight variation of the function. The only thing that's different is that instead of returning 0, we just return another copy of the same lambda expression that we also return as output. So now if you invoke this lambda expression, well, its first output will still be the number that we originally passed in, but the second output will just be a copy of the same lambda expression. So if we keep invoking it, we will never reach 0, so we will never reach the end of the sequence, and tada, we have an infinite sequence that repeats the same value indefinitely. But what if we want an infinite sequence that does something more interesting? So here's an example function that does something slightly more elaborate. Pause the video here and see if you can guess what this function does. Well, let's take a closer look. So this function returns this lambda expression, representing a lazy sequence. And the first output, which is of course the first element of our sequence, is the first input to this function. Okay. And then the second output, which is the rest of the list, okay, that's another lambda expression, representing another sequence. And the first output of that, which will now be the second element in our sequence, well, that's the second input of the function. But then the second output here, which is now the rest of the list after the second element, well, that's just a copy of the original lambda expression which produced the first element. So if you now invoke that again, you will get the first element again, and then another copy of this lambda. which will produce the second element again. I think you can see where this is going. What we get is a lazy sequence that alternates between two values that we've given, and again, it just never stops. I also made a version that cycles between 3 values, but if you want more than that, you're gonna have to write your own. Okay, but of course most lazy sequences that we'll be dealing with are gonna be finite. So let's see if we can write a simple function that will count how many elements are in a lazy sequence. Obviously, if the sequence is empty, then the count is 0. But if the sequence is not empty, then the answer is 1 more than the number of elements in the tail. So we just increment the result of a recursive call and then pass the tail into the recursive call. So we do need to invoke the lambda expression to split the sequence into head and tail, but unusually this time we're going to ignore the first output of the lambda expression, which is the head, and we're only going to care about the tail, which comes out here. And of course the tail needs to go straight into the recursive call. Finally, just add a declaration box at the top and we're done. Okay, how about this one? We can't do this with lists. I want to start at a value, x, and then just keep counting up indefinitely. So what does it take to do this? Well, we don't need a question mark this time because there is no condition. But we definitely want to return a lambda expression, so let's start with that. Now the input to the lambda expression, once again, we don't care. The first output to the lambda expression, which is the first element of our sequence, is going to be x because that's where we want to start at. And then the rest of the sequence is, again, an infinite sequence, but one starting at x plus 1. So we need a recursive call here. And we need to call it with 1 more than x, so let's increment x. And then just add the declaration box. Well, that was nice and easy, wasn't it? Let's try something a little more challenging. You can index into lists. You're definitely going to want to be able to index into a lazy sequence too. So let's create a function that will retrieve the nth element from a lazy sequence. But of course we start counting at 0, so the first element is element 0. What should this function do if the index is greater than the length of the sequence? Well, I'm going to give the function another parameter, which is a default value that it should return in that case. What if the sequence is empty? Well, then the index is always going to be out of range, so we just return the default value. Second possibility, what if the index is 0? Well, we now know that the sequence isn't empty, so index 0 is going to be the head element. In all other cases, we're going to need to call the function recursively. And the first argument to the recursive call is of course the rest of the sequence, which is the tail. The second argument is going to be the reduced index, so let's put a decrement function there. And the third argument is of course the default value. Okay, now looking at what we have here, it looks like we're going to need to connect this with this. So I'd be tempted to put a wire crossing function in here to put them together. But looking at the bigger picture, I noticed that it would actually be a lot easier if I could put the head at the top of the question mark function and put this entire block here on the left. Because then the head and tail would be right next to each other, and this def would also be right next to this def. So for that purpose, I'm going to write a variant of the question mark function, which is just going to swap the yes and the no. So here's the conditional operator that we wrote in video number 2, and here's an exact copy of it. So how do I need to change this so that it will return the right argument if the left argument is not equal to 0, and the down argument if the left argument is equal to 0? Well, the answer is I can literally just put this not box on the other wire here. And of course this function needs a new name, and since it's the Boolean opposite of the previous function, I'm going to use this character consisting of an exclamation point, which usually stands for a Boolean not, and the question mark. So back to our function, I can now change this to the new name of our function, and then I can shuffle things around in the way that I described. Now the head, of course, is the first output of the lambda expression, so let's invoke the lambda expression right here. And, well, it turns out that the tail is on the wrong side of this box, so this wasn't quite as convenient as I hoped, but we can still connect the two default values down here. But in order to connect the tail, we're gonna need to add a wire crossing function right here. Now let's draw the declaration box so we can see the geometry of the parameters. In counterclockwise order, what we want is the sequence, the index, and then the default value. Since there are two wires that need the sequence up here and down here, I'm going to add a wire crossing function here to pass the index to the other side. And then we can just join up the wires for the sequence. Now there are two wires that need the index here and here, so let's split this value into 2, and then let's just make a bit more space. And finally, to join up the default value wire, we need another wire crossing function, and I'm going to add that here. And then just for aesthetic purposes, I want to eliminate this kink here. Now that leaves only one wire unconnected, which is this one here. Now this is the input to the lambda expression, but you recall that for lazy sequences, we just don't care what the input is. So we could pass in anything that we want, so we could actually just split one of these wires and just pass it in there and not care. But for the purpose of making the code readable, I've decided on the convention of always passing in the number 0. And now we have a function that can retrieve any element at any index. But I want to make sure that the function actually works, so let's quickly write a program to test it. Let's start by passing in a sequence with just one element, and I'm just going to use 47 as that one element because it's the /. So for our first experiment, let's obtain element number 0, and for the default value, let's use 63 because that is the question mark. So what do we expect this program to output? Well, the / of course, because that's the first element in the sequence. But now let's see what happens if the index is too large. Now if we run the program, we expect to get the question mark, and ta-da, that's what we get. Okay, now let's try to use our first infinite sequence. Remember we wrote this function that will continually increase an integer and give you an infinite sequence of consecutive integers? Well, if we start with the number 40, then of course the 0th element will be a number 40. Well, let's look at element number 4, which will be 44, which we already know is the comma. Cool, so we can retrieve a single element from an infinite sequence. But what if I want to retrieve multiple elements, like let's say the first 5? So let's see if we can write a function that will truncate a lazy sequence after at most n elements. So if it's shorter, it'll just stay the same. So this function will take two parameters, the sequence and the number of elements that we want to truncate after. So the first thing to check, of course, is if the sequence is empty, because if it is, then we just return an empty sequence. Secondly, if the number of elements that we want to truncate after is 0, then we also return an empty sequence. And putting the head back on, of course, means we're creating a new lambda expression. The lambda expression doesn't care about its input. The first output from the lambda expression is, of course, the head. And then the second output, which is the new tail, needs to be the result of the recursive call. The first thing we pass into the recursive call is, of course, the tail. And the second one is n-1, so we need to decrement n. Now, to get the head, of course, we want to call the lambda expression that is the input sequence. And the tail of the sequence is going to come out the other side, so just like before, I'm going to put a wire crossing function in here to connect these up. Once again, the input to the lambda expression doesn't matter, so let's just pass in 0. And now let's connect up the sequence wires. And I suppose we might as well just put the declaration box right here. Then we need to liberate this n from this confine, so let's use a wire crossing function here. And then we just connect up the other n. And now we have a truncate function. Let's test it. Okay, so I'm going to use the truncate function on the same infinite sequence that we were looking at before. This time I'm going to start at 32, which is the space. And, well, there is only 2 arguments to the truncate function, so let's get rid of that. And let's take a look at the first 32 ASCII characters, shall we? But then, of course, we need to join these up into a single string. Now, fortunately, I have a string join function for that, which is pretty much the same as what you saw in the previous video, except for lazy sequences instead of lists. And we're going to use the empty string, aka 0, as a separator, so that we'll just get a single string of all those ASCII characters. Alright, time to run this. And ta-da, we get the first 32 ASCII characters. You can probably tell that I'm really excited about lazy sequences in Funciton. They allow us to do everything that lists can do, but more, because we can accommodate infinite sequences, and they have considerably better performance when dealing with a lot of data. So with that, we now finally have enough to write some actual Funciton programs, which I'm going to do to solve some programming challenges that I will find on the web. So this concludes my series. Well, almost. I'm still gonna make one more video in which I'm going to talk a little bit about the Funciton interpreter and also some extra information that I left out from the previous videos. And after that, I'm going to tackle Advent of Code 2023. See you then.